Good to go? All right. All right, guys. I'd like to thank y'all for coming. Today we're going to be talking about, or the title of my presentation is called Weaponizing Your Coffee Pot. Surprisingly enough, this has nothing to do with coffee or coffee pots. Let's go over the agenda. There's two parts. The first part is going to be kind of like why I wanted to do this or how this all started out. That's going to be split into two parts. First, we're going to talk about the Internet of Things, and then something I like to call the Internet of Malware. And then the second part is going to be more technical hacking, embedded system hacking, and for that we're going to be taking a look at two devices. The first is going to be the Belkin Wemu light switch appliance, which I'll explain, and then the Nest thermostat. And the Nest thermostat is kind of new. I just added the material last night, so it won't be as thorough as the Belkin stuff. And then we'll finish up with some good stuff. So first off, my name is Buentello. I'm a network security analyst. On my free time, I like to take things apart, and I like to call that debunking magic. And as you can tell, I'm getting better at putting things back together. Okay, so who here, by the way, either has one of these or knows what they are? This is a Nest thermostat. Okay, wow, a lot more than I expected. Okay, on that note, this is not a real object, by the way. This is something I made up, and I don't want to get anyone in trouble, so I'm going to name this a Frigidmore coffee pot. It has JavaScripts that control the taste of the coffee. It also is equipped with push notifications that lets you know when your coffee is ready. Now, the caveat to this product is that you need to run an Ethernet cable to connect it to the internet, which is not a big deal because I happen to have my router in my kitchen. So you get this coffee pot, you hook it up to the internet, and it has all these awesome features. Now, what if one day you're having some Wi-Fi issues and you look at what networks are broadcasting and you see this thing pop up? How would you feel about that? Now, who here would buy this product? Good. So keep that in mind going forward. So the first thing we're going to talk about is the why. The Internet of Things, it's kind of a big deal. It was mentioned a lot at CES this year, and a lot of people are doing it. So we all know that if one person follows through and it's something successful, that the rest usually come right behind it. But I know what you guys are telling me, right? These stuff has been here, right? We have these protocols like Z-Wave, ZigBee, and X10. What I'm telling you, these things aren't successful because they're closed. It needs to be something more universal, like TCP or IP or Bluetooth, because that's what my laptop speaks, that's what my phone speaks. The only way these things are going to become a commercial success is to employ these technologies, and that's what they're doing. For example, the Nest thermostat uses Wi-Fi, the Belkin Wemu uses Wi-Fi. It's also very cheap. So for example, the Belkin Wemu, by the way, this is the Belkin Wemu. It's essentially a light socket, or a socket that you plug something that you want to be controlled by your phone. And you can script it and do a whole bunch of other cool stuff. But for example, this has a $12 sock, and then it's also easy to develop for these embedded systems because most of the time they're running Linux. And it's a lot easier to find a Linux developer than it is to find a proprietary system developer. So again, these two things mixing together is going to lead to more proliferation of these products. So like you know, like the old adage, your parents used to say that your friend jumped off a bridge. Would you guys go jump off a bridge? Well, that's exactly what these guys are doing. They're jumping off the bridge, the Internet of Things bridge. And there we have on the, I guess, my upper left-hand corner is a connected light bulb, followed by a connected door lock, followed by a connected light switch, followed by a connected door lock, and then like this hub thing that connects to everything, and then a connected watch. And these are just the popular things that I could find on the internet. So continuing with that, we're going to talk about the Internet of Malware and what I mean by that. So everyone knows, whether you're a good guy or a bad guy, that the smarter these things become, the more vulnerabilities come along with it, because they're adding features as fast as they can, and usually security is a hindsight. You think about it last, and bad people take advantage of this tendency. And along with that is that there is no antivirus for these products. Does anybody see a click to uninstall button on this? There's no user feedback. There's no mouse. There's no keyboard. There's no monitor. So all this stuff mixed together makes it a very attractive avenue for bad guys. But it gets it gets worse with the cloud, however you want to see it. And what I mean by cloud, I know there's a big buzzword these days, but if you take a look at historically computers, 20 years ago when you used to buy a computer, you bought one maybe every 2 years because they had more memory, more graphics, and that was their monetization model, hardware. This model does not apply to these connected appliances. You're not going to buy a new thermostat every 2 years. You're not going to buy, a new light bulb. Well, you might buy it if it runs out, but you get my point. Is that they're not going to make their money off hardware, so they have to find some way to make money. And this is sort of undocumented because it's so new. But I fear they're going to make their money through a subscription type service, which is the cloud. And the cloud can go really bad really fast. I'm going to illustrate that right now. And for that, I'm going to tell you a story of the Nest thermostat. So anyone who out here who has this knows, I don't know if you ever bothered looking at, but how your thermostat updates. And the way it does is that automatically, kind of hidden behind the scenes from the user, it will update itself. Again, it is a convenience for you guys. You don't have to worry about it. There's no check for updates. When Nest arbitrarily decides to push an update, it's going to do it. So their architecture looks something like this. So you have a thermostat, and I have my phone in my house right there. And even though we're on the same network, it still communicates via this cloud, this Nest cloud that I keep referring to. And it does this, like I said, the Nest cloud is authoritative. It controls every function of this thermostat. So what if I'm a bad person, I'm not going to go after 1 or 2 thermostats. I'm going to go after that cloud. So what if a bad guy hijacks this cloud? We're going to call this skyjacking. He hijacks this cloud and decides to infect all these devices at once. Again, there's no check for updates. There's no revert to updates. Again, you can do really bad stuff if you control a device's firmware. And you basically turn all these guys into zombies. This is, again, a big difference from, like, let's say LinkedIn or Twitter or Facebook gets hacked. What happens then? You'll get an email to reset your passwords, or they'll erase, not erase, but they'll reset everyone's passwords for you. It's a simpler fix for that. But what happens when an appliance cloud gets skyjacked, which is what I just illustrated? They take control over this subscription service, and it just there's no way to revert, or there's no easy way for you to uninstall this bad stuff they did. So again, this is more as to why I want to do this. So there has to be a solution for this, right? There's no way they can just allow this to happen over and over again without coming up with some sort of insurance that can prevent this or mitigate for this. And I don't believe the answer is throwing money at it. So I want to highlight this directive that was part of the current administration's cyber directives, the list of directives that were put out. One of them proposed the formation of a cybersecurity insurance market. So that way when a Nest or Belkin's cloud or something happens with someone's in regards to cyber and security, that there's some sort of insurance that protects the entity from getting sued, from liability, from anything that happens resulting from a cyber attack. But this is not the solution. There has to be something better, because this is just going to lead to bad things happening. Along those notes, the real fear, at least on my behalf, I'm sure many of you guys, is that what happens when our vulnerabilities and our exploits start crossing a physical barrier? What I mean by that, there's a big difference from finding a SQL exploit that will dump a database from finding a water heater vulnerability that will blow up your water heater. Those are two different beasts. And what happens is the government usually reacts in a very bad way to these things. They usually react very drastically and very quickly. And that's something that it's illustrated by this statement: security through legislation. What that means is, don't improve products, don't put some sort of liability on the vendor. Instead, let's just outlaw it, because that's going to fix things, right? Well, all that does is criminalize the research I do, and I don't like that. And I'm sure many of you don't. So with that being said, I want to thank Josh and Nick and anyone else involved with the Cavalry for what they're doing and their efforts into protecting at least the research that we all do as a community. Another thing we can all do is you guys, right? Next time you buy something, take it apart. Don't just use it and take it for granted. Investigate how it works. What are the mechanisms of its insides? And ask the vendor questions. If something's not, if something's fishy, they should be willing to respond to you and settle any kind of worries you have. Okay, so that was the more rantish part of my talk. The second part is going to be a little bit more technical, and I kind of want to give a preface to why I even started with this endeavor, and hopefully that illustrated that. So I guess the point of this slide was to illustrate that embedded appliances are all around us. Now, these aren't necessary appliances, but they're still embedded systems, and they're in the most unobvious places. For example, that's the IME, which Travis Goodspeed and Michael Osmond turned into a spectrum analyzer. This is a kid's paging device, a toy, that they turned into a spectrum analyzer just because they decided to take it apart and mess with it. Same thing, Travis Goodspeed took a turning point RF clicker, which when I went to college was used for attendance and for like quizzes. They were able, or he was able to illustrate how someone could, jack this wireless network and like make it to where it's submitting the answers that everyone else is submitting. So I don't have to be in class. It's in class for me. And the third one here, the one in the middle with the little cartridge-looking thing, was actually a training that was put on this weekend by KF and Josh Thomas that showed how this little Leapster toy, it's a kid's toy, it's like a little Game Boy device, could basically hack it. It was running Linux, and they rooted the device. And one of the things he found out is that the serial access to the device, to access its insides, was exposed via the game cartridges. So he made that little contraption there where he soldered some wires to the game cartridge, and he was able to access it when he put the cartridge inside the device, and just totally take ownership of it. So with that being said, like I said, these things are everywhere, guys, and you just have to look for them and take them apart and see how they work. So the way this is going to work, this is going to be a very holistic overview, all the way from the hardware side to the software side of things. We're going to look at hardware enumeration, which is basically looking at a device to figure out kind of how it works, sort of. Then I'm going to talk to you how to get stuff in and out of this piece of hardware, because again, there's no Ethernet port you plug into. There's no USB. Well, sometimes there's USB, if you get lucky, but a lot of times there isn't. But so getting stuff in and out. We're also going to talk about unpacking its firmware and learning the structure of firmware. The next thing is going to be building binary. So these are not Intel machines that are running on these embedded systems. They're going to be running ARM or MIPS. So we're going to look at how we overcome this obstacle. And the last thing, very briefly, is going to be repacking it. And again, some of those obstacles that goes along with repacking firmware. Keep in mind that each one of these topics could be a talk on its own, and what I'm doing is putting them together. So there's going to be a lot of sort of skipping over what I'm going to do. But I found out the best way to do something like this was to pick a target and go along with it. So think of this think of this talk, or the next part of this talk, as a movie with commentary. So the main character in this movie is going to be this guy, the Belkin appliance. So I kind of alluded to this earlier, but what this thing does is you plug in a device. Again, it doesn't care. It could be a heater. In my case, a lamp. I mean, who knows? People plug weird things into sockets. So anything you plug into this socket, you can control with your phone. You can script it out. Again, this was a really neat device to work on. Okay, so the first thing I did was figure out how it works. Not from a hardware side, but from a software side. So the way this device works is you send a post message. You're on the network, you send a post message to it, and that one that you see highlighted could either be a 1 or a 0. The 1 meaning it's on, the 0 meaning it's off. So like any good hacker, the first thing I did was figure out how fast can this thing go. Thinking that they're going to limit this in firmware, right? There's no way they can just let this thing run super fast on and off. So for that, I want to show you what happened when I did that. And I doubt you'll be able to see the clicking sound, because there's a relay that goes on and off. But you'll be able to see the lights. And, that should illustrate it enough. So I'll go ahead and... All right. So that was it. So when I saw that, I was kind of, wow, this can't be good. But there were still a lot of obstacles I had. Like, for example, I had to be on the network for this to work. So what did I need? I needed persistence. I needed a way to be on there and, be away, be at Starbucks or be, halfway around the country and still be able to do this. So this is where our journey begins. This is where we start out with the task at hand, which is to hack this device and modify its firmware and get it working. So the first thing in this journey is hardware enumeration. What I mean by that is taking it apart, learning its structure, and sort of guessing where things are. The great thing about hardware, this is why I'm so attracted to hardware, is that, in software, if you want to debug something, you compile it in a certain way. Maybe you put some print statements in there and you compile it. Then when you go to production, you remove those print statements. Real simple process. You can't do that in hardware. You have to build a device that can be debugged in any step, whether it be in development, production, and these pads or this debug functionality, a lot of times is left on the device because of this. You can't just recompile hardware. It has to be remanufactured. So the job is to look for these debug interfaces on this device. And that's exactly what I found. Those 4 paths that are highlighted, or 2 of them at least, lead me to serial shell. So access to its sort of like the way you get shell on a Linux machine. It's a command prompt. So why is that important? Well, there are certain things that you can only get via shell. I can look at a piece of firmware all day long, but it will do me no good unless I see it running and doing stuff and interacting with the flash. So for example, you run mount on this device and you see these partitions. You can't see that in firmware or in the static analysis of the firmware. Okay, so good. I'm in the device. I can see stuff. One of the things that this Belkin device had was encrypted firmware. So I actually needed to go this route first. A lot of times the firmware is not encrypted and you can just look at it, just all willy-nilly. So this device, the firmware was encrypted, need keys to get that. Well, once I got shell access to it, I can start looking for these keys. Turns out they did have the keys on there. Not only the keys to decrypt the firmware, which you would expect, right? It has to update, it has to be able to decrypt the firmware, but they also left the keys to encrypt the firmware again, which made no sense. But again, this was on there. How do we get it out? Now, this is a patched WEMU, so it doesn't illustrate my point, but keep in mind that a lot of times these embedded devices will have read-only partitions because of size constraints. You can't just have a growing partition because some log file decides to go haywire. So a lot of times they'll limit it to read partitions only, but you'll almost always have a read and write partition. Why is that? Well, that's how it keeps settings of view. That's how, like, for example, web servers run off of. When you initialize the device, when you configure it, it has to have at least one partition that has read and write access to. So your job is to get stuff into there. So copy stuff from these read partitions into these read and write partitions, and then shuffle stuff out. So that's exactly what I did here. Is I got the keys from a read-only partition, put it into the web server partition, and then went to the website on my computer, and I got the keys out to decrypt it. Because there's something important I was going to say here, but I forgot. Oh yeah, but there's very novel ways of getting stuff out. And in fact, this was a very simple, kind of obvious way. But I was reading an article once where these guys found a way, I don't know if it's a camera or what exactly it was, but they found a way to get data out via the light bulb of the device. So they would make the light bulb blink on and off as ones or zeros, and that would be its firmware or whatever data they wanted to get out. So that was real neat. So again, you find creative ways to get stuff in and out. But again, that's the point. You get stuff in and out. Okay, so I got the keys. I decrypt the firmware. Now, what am I looking at? Now, this illustration doesn't belong to the WEMU. It's actually for the Nest thermostat, but it illustrates my point very well. That firmware is generally, not a strict rule, put into this format, where you have bootloaders, you have kernel, and you have file systems. Sometimes you can have multiple kernels, sometimes you can have multiple file systems, but generally you're looking for these divisions. And we have tools out there to help us find these divisions. One of them is Binwalk. Binwalk is a tool, can't think of the gentleman's name, but there's a link for it. It's an awesome tool that looks for signatures and files, and it gives you those divisions so that we can carve these file systems, these kernels, these bootloaders out and modify them, and then find out where to put them back together. It's also having some added functionality where you can look at data entropy. So like, for example, if portions of the device are encrypted and not the whole thing, you can look at the entropy of the data and find out where these divisions are and then work on them that way. So what this thing does right here, this script, it will look at the WEMU device and then find out where these divisions are, read those divisions, and automatically basically piece everything out and then mount the file system. This was a script I wrote to kind of automate things because doing it by hand was kind of time consuming. So once I carved out my file system, I mounted it, just like you would mount any other partition. And I noticed that it was missing a crucial binary that I needed, which was netcat. If I wanted to get reverse shell, yes, I could put SSH, yes, I could put telnet, but the easiest one by far is netcat. It doesn't have that many dependencies, and it's pretty easy to get a hold of the source. So I was missing netcat. I needed to get a hold of netcat. But there was a problem. This was not an Intel machine, or this was not an ARM machine where I had easy access to a compiler. This was a MIPS machine, completely different architecture from my own machine. So one of the things is that an obstacle, I guess, would be compiling for different architectures. How do you get past that? The greatest tool by far is going to be QEMU. QEMU is a virtualization technology, which I think VirtualBox is based off of. And it's great because it allows you to be any architecture out there, whether it be ARM, MIPS, and different variants of ARM, variants of MIPS. And you can virtualize a machine, remote into the machine, build your binary in there, and then get it out and put it back on your target device. There are some things you have to keep in mind. For example, your dependencies and the way you link it. So there's dynamic and static linking. Usually, you would think an embedded system, you might want to go dynamic because it results in a smaller binary. But that's a bad thing to do. You want to do a static just because you don't know what's on it. So when you compile it with static linking, one of the things is going to result in a very fat binary. But there's tricks you can do. For example, you can strip it. You can remove symbolic links. And there's a link I had that illustrates a whole bunch of other tools and tips to making static link files smaller. So now I have my binary, my netcat. What's next? Well, now I need to inject it into start. And you can, I appended this was a script that I run at startup on the WeMu that I think I added to the RC file. I forgot exactly where I put it at, but basically it would boot up and it would reverse shell back to me. And then I could run all those commands. So that 10.0.1.99 could be any IP. It could be an IP in China. It could be an IP of, in this case, it was a computer on the same network. But this is essentially what it did. All it did was go back to me wherever I was. So, there, I'm done, right? I got my binary, I got my firmware. Now I put all that junk back into the file system and I put it back together. And this is actually the easiest part, as you can probably guess that. The only thing is that you have to keep in mind is that a lot of times with these firmwares is there's integrity checking. This is an integrity solution, not a security solution. So it's generally trivial to find out how the CRC algorithm works. There's common standards for CRC, but usually the only thing you have to get a hold of is a polynomial they use, which probably the biggest help in any of this is going to be the developer page. Hopefully they're following the licensing, because if they're running Linux, they're going to have to be posting the source up. So you go there, find out what they're using, and you can get a lot of information from this page. So that's how I got the CRC validation algorithm. So I put back these parts, I append the CRC that it's looking for, and I continue. There's a problem though. How do I get the firmware on there? I need another vulnerability. And so remember that check for update feature it had? Turns out you can inject another string in there that will allow you to tell it where to get the said update. And exactly what that is right there, what's highlighted, is that within the check for update envelope, I guess, you add the URL where to get it at, and it will actually go and fetch it there. Again, this is unauthenticated. It just went out and got it all, just it trusted that it was secure. So it did that. The device, I sent this post message to the device. It went out, got the firmware, and we were done. Well, we had our I guess, compromised device. So now to our next target, the Nest thermostat. So remember that coffee pot I gave y'all an example of the beginning that was broadcasting this rogue Wi-Fi beacon? This is similar to what's going on with the Nest, or what I believe is going on with the Nest in regards to Zigbee. So Zigbee is a mesh protocol that's relatively new. It's a proprietary protocol similar to Bluetooth. It's not like a TCP/IP protocol. But here's the problem, is this Nest thermostat has two radios, Wi-Fi and Zigbee. This Zigbee is not mentioned in any spec sheet, any feature summary, nowhere. It's not acknowledged. So how do I know it's on or not on? How can I check this? At first, there was large speculation that this was going to be some sort of future product integration that they might do. But then they came out with these auto-tune features. And auto-tune basically works with select energy providers to tune your thermostat. So at peak energy times where rates are really high, it will turn down or up your thermostat. And how does this work? Were they sharing a database? Well, we know how smart meters work. We know they have Zigbee. Here's this device who has this unacknowledged Zigbee chip in it. It just makes sense they're using this back-end communication. So I started working on it. I started taking it apart. I started figuring out how it works. Then 2 days ago, they announced an API. Good news, right? They're going to talk about the Zigbee chip. They're going to talk about how it works. They're going to give me access to it. That wasn't the case. In fact, all they talked about was a web-based API, which is actually pretty cool. But still, it doesn't ease my worries that this thing is out there broadcasting Zigbee beacons without giving me some sort of an insight as to how it works. But I'm not the only one that's worrying about this. Home Automation Magazine has this line. Oh, and by the way, who, which happens to be the Nest product manager, would say nothing about the Zigbee radio that has been sitting dormant in the Nest since day one. Then again, Matt Rogers, which is a co-founder of the Nest thermostat, went on Reddit and didn't ask me anything. The second highest request was in regards to the Zigbee. Again, no answer. He gave no answer to it. Just completely ignored it. This wouldn't be that big of an issue if, for one, this didn't control a very powerful device, my air compressor, and my air conditioning system. Not just that, but the Nest, being as intelligent as it is, has a lot of data on board. Like, for example, it has a schedule of when I'm home and not. Because this is how it determines whether to turn the thermostat on or off. So this information is very valuable. And to a bad guy, it's really valuable. You can go ahead. Oh, go ahead. Okay. So yeah, it has a lot of data on board, such as the activity schedule of me. Not just that, it has access to what you're about to see right now, but the thermostat has two motion sensors, a near field sensor and a wide viewing angle sensor that can determine whether you're home or not. Like it can detect the difference between dogs and humans. So again, pretty advanced hardware that's on this thermostat. Go ahead. From your house out. Correct. Correct. And that's how I figured out it has the data on board, because it is not a requirement for the Nest to use Wi-Fi, but it's still smart and intelligent. That means, or you're about to see, but one of the things it has is a 2 gigabyte flash chip. 2 gigabytes for a 35 megabyte firmware makes no sense. Well, that's because a lot of the data has to be on the device itself in order to keep its intelligence without a Wi-Fi connection. But again, even if you're not using Wi-Fi, do we know what's really going on with the Zigbee and how it works? So again, this is going to be a very brief overview. I mean, very brief. I'm going to have a 50-minute video that I did this past week. It alone was over 50 minutes, so keep a lookout for that. But here we're going to go over some of the juicy bits about that. First off, this device is very advanced. It has two processors, an ARM application A processor, and then a Cortex M3 microcontroller. Again, 2 gigabytes of flash, Wi-Fi, and then it has an undocumented Zigbee chip, and then undocumented USB on the go interface. And I'm not going to talk about the USB on the go interface here, at least. If you want to know more about it, feel free to talk to me after the talk, and I'll explain to you why I put it on there. Also, the device's firmware is not encrypted, but it is signed. The signature is also enforced. So like I just described for the past 10 minutes, I'm going to use a similar methodology that I used for the Belkin Wemo. Let's look at the hardware. To the left of you, you're going to see these very, very, half a millimeter pitch pads, 16 positions, that on there we're going to find JTAG, we're going to find serial, and then we're going to find some very interesting pins, which I'll go over in a couple slides. But then to the right of you, see these pads there? Those pads are dedicated to the Zigbee radio. This was very odd to me. First I thought, okay, maybe it's for some FCC validation that they might be doing, but then the Wi-Fi radio doesn't have any of these pads. Why dedicate 10 whole pads to the Zigbee radio if you're not going to do something with them? I actually tapped these pads, and there's some initialization data on there, but there wasn't anything interesting that I can see from a hardware perspective. I needed to get serial access to the device and look at it. So now that was the next step. I illustrated those pins, I tapped into those pins, and then when it boots up, I see this. For anyone that's seen U-boot before knows that there's a lot missing. I'm missing the kernel messages, I'm missing the U-boot messages, and this is bad stuff. So, kind of sidetracking from my methodology, I started looking at the firmware, and I started looking at U-boot specifically. So within U-boot, there's these directives. The first one I'm going to go over, and then, by the way, this is the U-boot binary that I reverse engineered. The first is boot delay equals 0. Part of U-boot is, one of the features U-boot gives you is to interrupt its sequence, its startup sequence. Similar to the way BIOS would give you F10 or escape or whatever to select boot device, U-boot does the same thing. You can hit a break sequence or space bar or something, you can stop its sequence and change its directives. The whole purpose of U-boot is a bootloader to load the kernel file system. So again, if I could have just stopped it, I could have changed it. Unfortunately, that boot delay equals 0 prevents me from doing that. So that's the first directive that I don't like. The second directive is, is that add quiet directive. What that does is very similar to the way grub works in Linux. You add quiet to the kernel loading directive, and it silences any kernel messages, which is extremely vital if there's any kind of security mechanism, such as signed binaries. You need access to the kernel messages. Again, that's being silenced by that quiet statement. And then the last thing I highlight is the silent equals 1. Basically, U-boot is being compiled in such a way as to it itself is not giving me any messages. Again, I can take care of this. I patched the bootloader. I re-upload the firmware, but it didn't work. And that's because it's signed. I was kind of hoping that they weren't enforcing that, but they were, and my efforts were futile. So some other notes, and this is where I'm going. So those pins on the left side, the interesting pin I was referring to was there is a boot selection pin on the device. So that way, if you toggle it high or low, it changes the way it boots up. And this is done in hardware versus the way U-boot was done in software. There's no way that it can be updated. So I don't mind discussing it. You pull the pin high, and it changes its boot sequence. And depending on whether it's a warm reset or a hard reset, that matters a lot. So again, I'll leave you guys with that. If you have any questions, feel free to talk to me after the talk, and I can give you more information about the thermostat and its insides. Okay, so now for our finale, for the end. My message to you guys is to take things apart. Look everywhere. This stuff is not very difficult to find and not very difficult to practice on. That is a thrift store there that for a lot of my hardware I go look at, because you find a bunch of cool stuff there. Things that people throw away that, who knows, it might be broken, and all you have to do is fix it, and you still feel like you accomplished something. So again, thrift stores are awesome. If anyone took the hacking workshop this past weekend on the Leapster device, I asked KF, how do you get the idea to operate on this Game Boy device? And he said he just went to Toys R Us and just looked, bought pretty much one of everything and found out. I'm not saying go and buy one of everything, but he just went out there and got lucky and found this toy that had it that didn't cost a $250 thermostat. Also, I thank DerbyCon for having me here, and the motto here is all in the family, and I truly believe in that statement. I have a passion for what I do, and I'm sure every speaker up here has a passion for what they do, because if they didn't, they wouldn't be up here. And I guess it makes sense. If I have a passion for what I do, I love talking about it. So if for some reason you can't talk to me after the talk, feel free to reach out to me. I'm going to put my contact info out there, and just hit me up. If you're working on a Nest, if you're working on a router, if you're working on a cable box, whatever you're working on, and you can't find any help, who knows? I might be able to help you, I might not. I want to give a special thanks to TXRX Labs, which is the hackerspace in Houston. If any of y'all are ever in Houston and want to hang out with me, this is usually where I'm at. And I say that because Houston SecCon is coming up. So if any of you guys are going to that, again, feel free to send me a message. There's my contact information if you guys want to reach out to me. I think that's it. Any questions? Any questions? Yes? Okay. Okay, so the question was, how was I able to discern that pin modified the boot sequence? Long story short, I had to take one apart. So what I mean by that is I lifted the chips off the board, and I reverse engineered the pin out. And this is because if you look at the thermostat here, you see all those tiny gold dots. You can hardly see them. But this makes it very difficult to reverse engineer hardware because you don't know what's going on, and you can't test all these pins. So the best way to go about attacking this would be to lift the chips off the board and work backwards. So what I noticed is that there was a power rail, which made no sense, right? Why do I need access to a power rail? But right next to that power rail was that boot pin. So you jump the boot pin to the power rail, and there you go. You modify the boot sequence. Yes. Something similar to that. Yes. Within a day, I had to buy another one. But yes, for about a day, it was by itself. Yeah. I don't know. This was very similar to that. Okay, so that Belkin device was actually. I guess I should also thank my brother because that wasn't mine. That was my brother's. he got it for Christmas, and so this was back in January. He got it for Christmas, and I was actually working on another vulnerability for iPhones. And I did a network scan of my network, and I found this device broadcasting port 53 was open, DNS. So immediately the lights went off in my head that what the hell is this device? I know everything on my network. What's going on? Well, it turns out he had plugged it in and set it up without notifying me. And that's how it all started. So I still owe him one, but yes, it was told by sheer luck, I guess. Any questions? Good? All right. Hmm? Oh, so that's a little bit of kind of just well, actually, I have an article on my blog about it, but it's sort of you just hardware has been the same. Hardware protocols have been the same for the last 20 years. They don't update like Python or anything else. So you just look at what their tendencies are. So for example, one of the things you find first are all the ground ones, and you do that with like a continuity test. So you can find the pinouts of these devices with just a multimeter. You don't need any expensive equipment like an oscilloscope or a signal generator or anything. Most of the stuff you find with a multimeter. Just simple tendencies. Yeah, yeah. Look for a tone. Like for example, transmit will at the beginning of a booting will fluctuate between a voltage of 1.8 to ground. So you look for this up and down, up and down, up and down, and your multimeter will look like it's freaking out. But generally, that will indicate that data. That's data. So then you get the voltages and you look at it. Yeah. Any other questions? All right. Thank you guys for sitting here with me, and I appreciate it. What's going on, man?